let me show you this. The simple reasoning task is a task which it demonstrates a fairly basic form of reasoning within the NECS, and it was written mainly in order to show you a couple of a couple of ways of setting up, or a simple way of setting up the NECS. The way this is set up is we have a hot field network in the bottom level, okay, and it's going to act as an associative memory network. We've got 4 associative rules in the top level, which are going to link together knowledge or these declarative chunks in the GKS, and so show some chaining of reasoning. All right, and then we have 30 dimension value pairs that are initiated. The 30 dimension value pairs from which we generate 5 unique patterns that represent, let's say, some sort of featurized representation of each one of these 5 declarative chunks. And then we encode these patterns into the hot field network. We create a rule that says if chunk X, then infer chunk X plus 1. So if we're talking about chunk 1, then infer chunk 2, and so on and so forth. And then the actual reasoning, okay, it performs 2 rounds of reasoning. Both the bottom and top level are set on. Each pattern is given with some amount of noise to set up as input into the reasoning. And what we receive at each timestamp is 2 types of outcomes. First, what we receive is the chunk, which is a reconstruction from the auto associative memory network in the bottom level, a reconstruction of the chunk related to the pattern. Remember, our input is the pattern, but it's noisy, which means we've zeroed out a certain portion of the pattern. So it's only a partial pattern. So what the bottom level is doing is it's rebuilding that pattern. So it's inferring the chunk, the full chunk, the full pattern, reconstructing the full pattern based off of this partial activation. And then once that chunk has been concluded by that bottom level network, the associative rule in the top level says if that chunk, then infer the other chunk. So what you get back is that reconstructed first chunk, and the one and the next chunk in the sequence. So for example, if the input was constructed based on the partial of pattern 1, then the conclusion would be the chunks representing patterns 1 and 2. So let's see that in action. So you've got here's our patterns. What I've done is I've just named the DV pairs 1 to 30, okay, and I've set this up. There's no particular organization to these patterns, except for the fact that each pattern is a unique pattern. Okay, there's not any. There's certainly overlaps in the features, but there aren't. Each pattern is uniquely defined. This is our number of nodes, just a way to keep track of how many DV pairs we're actually generating. And here's our noise. The noise is how much we're going to apply for the input. One thing to note here is that noise is not applied to the input in the conventional sense, i.e. randomly. Instead, what happens is that the percentage of the pattern that gets it just represents the percentage of the pattern that gets zeroed out. So, for example, the default of 0.4 means that the first 60% of the input will be constructed using the pattern, but after that, all of the dimension value pairs for the last 40% are going to be zeroed out. You can't really go any higher than about 50% noise. If you go above about 50% noise, what's going to happen is that your autoencoder will not have enough of the pattern to be able to correctly reconstruct it, to settle on the correct pattern. I mean, if you have any knowledge of how a hot field network works, you do need to have a certain amount of activation, a certain amount of a pattern in order for it to be able to correctly fall towards the correct encoding, the correct position on the network. Be able to find, fall into its correct space where the pattern has been encoded. Setting up is fairly straightforward. We have our reasoner. We initialize the world. I'll show you that in a second. We add some knowledge to our reasoner. We're going to give our reasoner all of its knowledge, which is basically our 5 patterns. The chunks represent, remember, each pattern is assigned to a chunk. We'll then set up a hop field network. The hop field network is going to have all 30 of our nodes, all 30 of the dimension value pairs, the features of the chunks. We'll then encode our hop field network, which means we'll encode our particular patterns into our hop field network. We'll set up some rules. We'll do two rounds of 2 reasoning iterations, and we'll make the conclusion threshold 1, which means that only fully matched conclusions are going to be returned, and then we'll have it do some reasoning and die. And we'll actually look at this. We'll demonstrate this task. I believe I fixed it as of last time. Remember last semester, Emily and Shane, remember we had some issues getting it to work. I think that's been fixed. If it's not, then it means another thing for us to do. So, in this particular case, we use something which is called a distributed dimension value pair. Okay. Now, a distributed dimension value pair is simply just a pair where we don't particularly care. What it is. It's basically just a generically defined dimension value pair. What it is really is it's a way of defining essentially neurons. So if you want to, let's say, randomly encode, instead of encoding a particular chunk with some sort of explicitly defined feature, but instead you just want to define it by a random distribution of nodes. The distributed dimension value pairs are the things which allow you to define generically defined or nodes, let's say for hop field network, or for some featureized representation where you don't really care what the features themselves are. It's just it's a way of, let's say, assigning a pattern of activation. If you're trying to correlate this with neural activity, it's a way of assigning a pattern of activation to a piece of declarative knowledge without actually having to define some sort of feature set for that declarative chunk. All right, so anyways, we set up 30 of those, one for each node. We then are going to go through and create our declarative chunks based off of the patterns. All right, and then we are going to set the correct DV pairs within those chunks based off of the patterns again. All right, so one other thing to point out is that there's whenever you're creating a declarative chunk, and this is actually true for any type of chunk, but it's especially true for a declarative chunk. What a declarative chunk will create, along with creating whenever you create a declarative chunk, if you assign a declarative chunk a label, if you give it a name, okay, what it'll do is, on top of creating a chunk, is it'll also place inside of itself something which is called a semantic label. A semantic label is basically just a dimension value pair that has a semantic that has the name of the chunk, the label of the chunk within it. Now, sometimes you want, for your own convenience, to name a chunk, but you don't necessarily want that chunk to have the semantic label within it, which means I don't want that particular chunk to be plain. I don't want that particular semantic label to be plain a part of whatever task I'm looking at. So in this case, I have these chunks which I'm naming 1 to 5 in terms of the patterns, but I don't want to have a semantic label of 1 to 5 actually being part of the chunk, because it messes with the pattern itself, right? Our pattern is already defined for us If we add in the semantic label, then we've already got another node which is playing a part, acting as another feature for this chunk. So we can actually we can tell it not to generate the semantic label, or excuse me, not to add the semantic label into the chunk itself. And that's just an option right here, add semantic label, and you just specify it as false. That's just to let you know about that particular option. So let's get down to the encoding of the hot field network. Now, like in our previous example of our previous identification task example, the hot field network also uses the implicit component initializer. One of the things it does differently, though, than the identification task is this uses a different method within the implicit component initializer. That is, it uses a method which is called encode. Training a hot field network, or training something which is what we call an autoencoder, is a little bit different than training, let's say, a backpropagation network, where you give it an input pattern, you give it a desired output, and it'll learn based off of it'll learn to correlate the input pattern and the desired output. With an autoencoder, all you do is you give it a pattern, and you tell it to encode that pattern, and then it will encode the pattern. So for things like hot field networks where you have an autoencoder, the implicit component pretrainer has a method that will allow you to easily encode a hot field network, or a network, and then test it. Now in this case, though, we're not going to necessarily use its built-in termination conditions, because in this particular case, we actually want to use different transmission options for the hot field network. Now, a hot field network, I don't know if you're familiar with a hot field network, is that it's a fully connected network, which means all of the nodes are connected to one another. And what we do in order to determine when a network is finished is we have to let the thing go for a certain amount of time, and then decide at a certain point of it kind of spinning itself in circles, or letting the activations go in between all the different nodes, when it's reached kind of its endpoint, when it's settled into a certain spot. So that's called a transmission option, and in this particular case, what we want to do is we actually want to use a different transmission option for training it than for testing it. So when we train it, we're going to actually just let it go for n spins, and the n is defined by the number of transmission spins parameter. In this case, we're just going to use the default, and we're just going to let it run, do that number of spins, and we'll let it do that number of spins on all of the different patterns. And then what we're going to do is we're going to let it encode. So here's really easy. All we've done is we set up the network before. Remember, we gave it a bunch of inputs. And what we do here is we set it to this n spins. What we're doing is this is essentially setting up our data set, like what we've done in our previous example, in the identification task example. So we're setting up a bunch of different data sets. Each data set is going to be one of the declarative chunks. We can set the pattern simply by taking the declarative chunk and adding the range. This right here, by the way, this add range is why we specifically said not to put in the semantic label. Otherwise, it would have also added the semantic label as being one of the nodes within this pattern, and we would have never gotten it correctly to encode. And then we'll just add it to our list, and at the end, to encode this, we're basically say implicit component dot encode, when we'll pass it in the network that's going to be used to encode, and the data set. We don't need to give it a trainer because it's not training, it's just encoding pattern. So here is the target, here's the data set, here are the patterns we want you to do. And then we have some options like when do you want to terminate? All right, do you want to terminate after a certain number of spins? Do you want to let it set, or do you want to terminate after a certain success rate? In this particular case, we wanted to wait until everything is encoded, but we do have a couple of different options, and I'll show you those options. The two options are for a fixed number of cycles, so go for a fixed number of repetitions through each of the patterns, or wait until, or return back once everything is successfully encoded. And so basically the way that works is that it does a phase of encoding in which it encodes, and then it goes and it tests the patterns and sees if it can correctly recall the patterns. All right. So that's how the encode works. Your other options within there is, if you want to go for a fixed number of times, how many iterations do you want to go through each of the patterns? You can also choose whether or not you want to do a random traversal, and then you can also specify to test only. Now in this particular case, like I said, we are wanting to use two different transmission options. There's no real way for us to change this inside. Okay, this is a specific thing for a hot field network. This is why we've separated this out into two different phases. So in the first phase, we're encoding. I want to use the end spins to encode, so I encode right here. But when I'm actually wanting to check to see how well it's doing in terms of being able to reconstruct the patterns, what I'm going to do is I'm going to change it to a let settle. I'm going to say let the thing go until it settles into a pattern, and then what I want to know is what the accuracy was. So I can still use this encoder. I can pass back in the net and the SIs, but I can tell it to only test. Say, so instead, just test, and then tell me what the accuracy was. Now, both of these will pass back accuracies. In the case of the train, what comes back out from the train function is the sum of squared error. Okay? What comes out from the encode encode is the accuracy. So how accurately the network encoded all of the patterns. So the reason why we do this, you say, well, doesn't this not exit out until they're all successfully encoded? Yes, it doesn't come out until they're all successfully encoded. But remember, it's only doing n number, and I believe n, I think by default is 100 or something like that. It only does 100 spins, okay? And it's not necessarily testing. It's just going through and doing an encode, doing an encode, doing an encode for 100 spins, and then passing it back out, saying, okay, I've now successfully encoded all of these given your parameters. Okay, let's settle though can sometimes have a different behavior, meaning that I go for 100 spins and that's enough to encode it in the end spins, but if I let it fully settle, maybe it actually settles into a different pattern. Okay, while it will say, okay, I encoded this, when you try to let the thing settle, it'll settle into a different pattern. So this is just giving us a more online way of testing afterward to make sure that the network actually settles into the things that we've encoded. So it'll check it a second time, check for the accuracy, and it waits until the accuracy is equal to 100. What you'll find, or what you'll see when we actually run this, is that it actually encodes the patterns correctly the first time. So it's actually very good at this, and encodes very quickly. But if you were talking about more complex patterns, this might be a good check to do. And it's also something that once learning has been implemented, or offline learning or knowledge integration has been added into the NACS, that the system actually will be doing something very similar to this on its own anyways. So, okay, moving on. This right here sets up the rules. The rules are fairly simple. We're using a refinable associative rule. It sets up very similar to how we set up action rules in the top level of the ACS. But of course, we just call initialize associative rule instead. We're passing it the agent, who's a reasoner. We're passing it the factory to create it. And then, of course, we're passing it the conclusion chunk. Now, remember, it's not an action in an associative rule. It's a conclusion. In this case, the conclusion is going to be I plus 1. And the generalized condition will have within it the chunk. I. Remember, the idea was the associative rules will say if chunk x, then infer chunk x plus 1. So this is just setting that up. And of course, it's doing a count minus 1 because, of course, if you're at the last chunk in the pattern, you can't go go beyond that because there are no more x+1 chunks. All right, then we commit the rule to the reasoner, fairly straightforward. All right, so in the do reasoning, the actual doing of the reasoning, we go through each of the chunks. We're going to create a new data set. Now in this case, our agent, what this simple reasoner is going to demonstrate is a way for you to shortcut the ACS-NACS kind of interaction. So agents, the way you can just use the NACS, and now this is an option, if you want to just look at a task that's just using the NACS, you can choose to, instead of having something perceived, we have exposed in the library a function in the NACS that you can call directly. And you basically, it's called perform reasoning, and you pass it in just the pattern, the input pattern, and what it gives back to you is the conclusions. All right? It's a way for you to just test out the NACS, and that's what we're using here. So we're not integrating in the NACS, we're not wiring the whole thing in, so we're not having it perceive and wait for an action or anything like that. We're just looking at how the NACS itself is performing. So in this case, I don't actually have to use sensory information, although you certainly still can. But I create an SI, I can use my initializer. The implicit component initializer does have a new data set. The other thing I'm going to point out here, and this was done after realizing that it was necessary. This is the only class within the entire library where you can actually do this. Okay, but activation. You can call the default constructor. Oh, I'll call this SI2. You can call the default constructor of the activation collection. Okay. You can also use this command as well, which all basically does the same thing. It just generates an activation collection for you. It's just for the necessity of customizing, of doing customization. This particular class, it's okay for you to be able to generate in this kind of more standard type way. Okay. Anyways, you generate the activation collection, and then I populate it. What I'm doing here is basically the same thing I do with a regular SI. The reason why you see this SI, the reason why you see this regular, the activation collection, why I've called it SI, is remember I may have mentioned this before, activation collection is actually the base class for a sensory information, because the sensory information is an activation collection. What I mean when I say activation collection is it's a bunch of dimension value pairs or objects within the world, and associated activations for them. So it's a collection of activations. But you can use this root one as well. And what we're going to do here is we're going to go through and we're going to fill in the pattern up until the point at which we get to the noise level, and then we'll zero out the rest of the pattern within the sensory information. We then pass it as input into the reasoner just by saying reasoner.nacs.perform reasoning, and we just pass it the input pattern. And what we get out from it is we get out a thing called a chunk tuple. And you say, well, what is a chunk tuple? A chunk tuple is really simple. We get out a collection of chunk tuples in this case. But you ask, what is a chunk tuple? A chunk tuple is very easy, okay? It's a chunk and the activation of the chunk, okay? It's like an activation collection, but it's specific just to chunks. And what it just says is, in the case that we use it here, is that this particular chunk has an activation. It'll say for this particular chunk, we have this particular activation. And so the stuff that comes out in it, if you were to see what's in a chunk tuple, it's simple. We've got an activation for the chunk. We've got the chunk itself, okay, and then we've got also a timestamp, which is just associated with when that particular chunk was concluded. It's information that you may find interesting from the outside, but it's actually more interesting from an under the hood type of thing, so that the system knows when to put those chunks working memory. Okay, so what we do here is we're actually going to iterate through the conclusions, see what our conclusions were from reasoning, and then we'll also check our retrieval accuracy. If the chunk was what we thought it should be, if the pattern was what we thought it should be, then we're going to look at our accuracies. Here also are some other tasks. I'm going to show you these. These next three I'm going to show you. Now the setups are very similar to what we looked at just now in this simple reasoner task. But these particular simulations were done by a student last semester. Dan Cannon is his name. And he looked at how to do, I'm trying to think, it was, he was looking at how to model inductive reasoning. Now, this is chapter 11 in the computational psychology book by Ron Sun. Chapter 11 is on inductive reasoning, and it looks at a bunch of different types of inductive reasoning. Now, it was looking at typicality effects in inductive reasoning, similarity effects, diversity effects, and background knowledge effects. And he was able to, in a very simple way, actually demonstrate all of these different effects. So I'm going to see how many of these I can show, and hopefully, I think I should be able to show all of them here. So I'll start with typicality effects. Now, typicality effects has to do with how typical a particular object is, or a particular object is when it's related to a higher category. So, for example, you ask questions along the lines of which is more representative of a bird, a robin, or a penguin? And what we would expect people to say is, of course, that a robin is more representative of a bird. The idea here being that a robin actually has more features in common with what is typically defined as a bird than what a penguin has with what is typically defined as a bird. So here we can set up a pattern for a bird, we set one up for a robin, and we set one up for a penguin, and what we see here is if we run it, that we'll get that down in the bottom, an answer as to whether or not robins or birds are more typical of one another. Now, to set this up, it's actually fairly simple because you don't actually need a hot field network in the bottom level or rules in the top level. This NACS, this can actually be captured simply by using the top-down and the bottom-up activation capabilities within the left and the right-hand sides of the NACS. So we can set up an agent. We can add up all of the knowledge representing the bird, the robin, and the penguin into the GKS in the NACS. We only need to do one round of reasoning. We can have it do the reasoning and then be done. Now, what we'll do here is we will, and let's see here. In this, basically what we'll do is we will set up both a robin as an input and a bird, or excuse me, a robin as an input, and then separately a penguin as an input. So it's going to do two different reasonings. So first we'll set up a robin, all right, and then we'll have it do reasoning. Then we'll have it set up then we'll have it go and set up the, where is this? I guess it's just doing it separately for both. So we'll set up a robin, and then we'll capture what its output from reasoning is. Then we'll set up a oh, excuse me, I had this backwards. I'm sorry. In this particular task, I'm sorry, we set up the pattern for a bird, and we pass in the pattern for the bird. And what we're going to look at is we're going to look at what the activations of the two chunks that come out, the robin or the penguin. And whichever one is more activated, we'll say is more typical of that particular thing. Okay, so what we do is we pass in the activations for the bird, and what we'll get back out is we'll get back out activations for both the robin and for both the robin and for a penguin. And then what we'll determine is if one activation is bigger than the other, then one is more typical than the other. All right, so the similarity effect says that two things are considered to be more similar if they have more features in common. So in this particular case, you would have robins, sparrows, and geese. And what you would test is robins and sparrows. What you would do is you're trying to see what is more similar to a robin, a sparrow, or geese. And so you pass in a robin, and you look at the activation of a sparrow, and you look at the activation of geese. All right, it's very similar to what we did before. All right, we put in that. What we get out is the similarity to a robin. Okay, and then you determine that sparrows are more similar to robins than geese, or geese are more similar to robins and sparrows. So here's a similarity effect. There we go. So this is true. So when you pass in the activation for you're passing in the activation for a sparrow. It has a beak. It's a bird. It builds a nest. It flies south for the winter. Lays eggs. It's red, small, has wings. All right. What you get out is, of course, you get out the sparrow as the chunk. All right. And its similarity is 90% similar to a robin. Whereas, and you also get out geese, but it only has a 62% similarity to a robin. And so what you say is, therefore, sparrows are more similar to robins than geese. Glad to see that one. Okay, diversity effects. Now, diversity effects has to do with when combining two things together. Okay, the question basically is what you're trying to find out is which of two statements or which of two items are more strongly related to a mammal. And I can't remember exactly how the question was asked. But basically the idea behind a diversity effect is that when a hippo is combined together with a hamster, all right, people will more often say that hippos and hamsters are more stereotypical of mammals than hippos and rhinos. Let me see if that's the way we say it. So hippos and hamsters are more diverse mammals than hippos and rhinos, or that hippos and rhinos are more diverse mammals than hamsters. The idea is that they more strongly define a mammal. The idea here being having to do with the diversity effect, meaning that hippos and rhinos are very similar to each other, which means they have a lot of overlapping features when we're talking about features that define a mammal. The idea being that you have a bunch of features which will define a mammal. Okay, hippos and rhinos will only activate this segment of a mammal, all right, of the category of a mammal, whereas hippos and hamsters will activate this much, because let's say if this is the set of information that defines a hippo, and this is the set that defines a rhino, there's a lot of overlap. Whereas hippos and hamsters, there's only a little bit of overlap. So when we combine together all of the values in both of those circles, you'll have more nodes that are being activated by hippos and hamsters than would be activated by hippos and rhinos, because hippos and rhinos are activating a lot of the same features. So if you were to run this, what you should get out of here is that hippos and rhinos, or hippos and hamsters, are more diverse than hippos and rhinos. And so what we'll see here, okay, is that we pass it. What we're going to do is each time around is we're going to pass in the features for hippos and rhinos. So here's our features for hippos and rhinos. Okay, and then the output from the reasoner we're going to pass out. We're going to look at is the mammal chunk. Okay, so we expect hippos and rhinos, of course, to come back as well as conclusions, but we're also going to look and see how much activated the chunk for a mammal is. Now, in the case of hippos and rhinos, we've activated all of the features related to hippos and rhinos. And what we'll get out is a 6.5% activation of mammal for hippos and rhinos. Now we'll pass in hippos and hamsters. All right, now we'll pass in hippos and hamsters, and what we'll get out in terms of the mammal is a much higher value, so we get an 82% activation for hippos and hamsters. And of course, hippos and hamsters get fully activated there as well. And so what we see is that hippos and hamsters create a higher activation for mammals than hippos and rhinos. Therefore, hippos and hamsters can seem to be more related to mammals than hippos and rhinos. Now, of course, obviously, they're all related equally to hippos or to mammals. But what the diversity effect has shown is that if you give people or require people to make the choice, which of these two are more indicative of mammals, they will make their reasoning based off of this diversity effect, which means hippos and hamsters will get a higher activation than hippos and rhinos. All right, the last one is a background knowledge effect. The idea here being that a lot of association has to do with context, and has to do with your background knowledge within a context. So in this particular example, we're looking at bears and whales, okay, or bears, whales, and tuna, okay. And what we're trying to find out is under what situations do two of them equate to each other in one way, and in what situation do the two of them equate to each other in another way. That means that, so for example, if I was to be asking the question of blank and blank live in water, okay, and I want to know which statement is stronger, that tunas and whales live in water or tunas and bears live in water, or I'm asking the question of whether or not they eat fish, okay, then I'm going to get different answers based on background knowledge. So what I'm asking is which statement is stronger? Tunas and whales live in water, or or whales and bears live in water. All right, so I put both of these up here, and you have to respond which statement is stronger. And of course, in the case of lives in water, you would say tuna and whale is the stronger, right? But if I were to say eats fish, which would be stronger for you? It would be whales and bears, okay? So it's all a matter of background knowledge. The idea being that you have background knowledge within you, that there's an association between the concept of living in water and the activation of a whale as well as a tuna, right? Both of these are kind of associated with tunas, and they're associated with whales. And to a lesser extent, they're also associated with bears because, bears live around streams and they can hold their breath underwater for a long time. So there is an association between them as well. But there's also a much stronger association between the idea of lives in water is going to much more strongly activate in the bottom level of the NECS a tuna and a whale when it's presented, and it will, let's say, a bear. So in the case where we're working with, so what we can do is we can capture that in the bottom level by using a backpropagating network. Now this is different than the Hopfield network. This is a heteroassociative encoder. It's encoding associations based off of frequency in which they appear in conjunction. Okay, it's not necessarily the case that a whale will be defined by eating fish and by living in water, but instead be associatively linked, meaning that the concept of living in water or the concept of eating fish will be more often associated with a whale, a bear, or a tuna, or differentially associated with it. And you can capture that using a neural network in the bottom level. So we can set up as our input lives in water and eats fish, these two different concepts. And we can set up as our output either a tuna, a whale, or a bear. We can go ahead and train this neural network, okay, to report things based off of there being a higher associations in the correct direction. And then if we then go and run the task, we can pass in simply the question of, or the information of either lives in water, or the information of eats fish. And what we should see come out is tunas and whales are more likely to live in water than whales and bears, or we'll see come out that tunas and whales, or bears and whales, are more likely to eat fish than whales and tuna. So I'm not going to run this particular one just because it takes a little while to train the neural network, but that's the output you would expect to see, and sure enough in this you do see that.